Hello everyone, my name is Marco Endek and I would like to welcome you to my presentation about CCD sensors. First of all, if you have any questions during my presentation, don't hesitate to note them and write me an email afterwards. Let's go! All cameras today, in smartphones or DSLRs, base on CCD or CMOS sensors as their key component. Since the beginning of the 21st century, these sensors replaced photographic films very quick. There is a small technological difference between CCD and CMOS sensors, but a lot of my today's content is valid for both types of sensors. A CCD is a light-sensitive semiconductor component. It consists of many light-sensitive pixels ordered in a two-dimensional array where each pixel has a quite similar working principle to a photodiode. The light particles, called photons, can free electrons from the semiconductor material and result in a measurable change of the electronic charge. Let us see this process on a sketch. Here we see a Vance model of a semiconductor with its conduction and its valence band. Between those two bands are forbidden energy levels, also called band gap, with its value Wg. Now we irradiate this material with light. Photons with the energy Wph will hit the material. The energy of the photons, Wph, can be calculated with the value of the Planck effect quantum, a natural constant, multiplied with the frequency of the light. Or where the frequency of the light is the speed of light, another natural constant, divided by the wavelength of the light. If the energy of the photons is higher than the energy of the bandgap, the light can free electrons from the valence band to the conduction band. This effect is called the inner photoelectric effect and was discovered by Albert Einstein. By the way, Albert Einstein got his Nobel Prize in 1921 for the photoelectric effect, surprisingly not for his specific relativity theory. For an easy understanding, the function behind a CCD sensor is often explained with a bucket model. One bucket illustrates one pixel. The buckets collect the photons like rain at a specific location, and after a certain time the collected water can be shifted, measured and processed. In reality, not every photon frees an electron. That's the reason why the quantum efficiency of a CCD sensor is such an important value. If you take a look in a datasheet of a CCD sensor, you can see that the quantum efficiency is dependent on the wavelengths and need to be considered by the processing. After the photon to electron conversion, the total accumulated electrons are shifted clock by clock to the next pixel until they reach the readout count. Next, the weak photoelectric voltage gets amplified to being processed. In photography, the value of amplification is adjusted by the ISO value. After the amplification, the analog voltage is translated in a digital binary value via an analog digital converter, also called ADC. So finally, each pixel of the two-dimensional array has a binary value according to the process before. This way we would get a black and white picture. To get a colored picture, filters are used. Like I mentioned before, CCD and CMOS sensors are used in nearly every camera today. They are a typical example for a sensor, as on the one hand they convert light into electrons per pixel first, and on the other hand they make it possible to represent the gained information in a two-dimensional array so that we finally receive a picture. Much thanks for your attention and see you soon. Goodbye.